Okay, so some of you are in line. Hi everyone. I hope everything is okay for you and you are well prepared for this new period of confinement. Just start with this third lecture of thermodynamics and propulsion system. So for today, as I mentioned, the topic is about the combustion process and specifically the one that are occurring in air breathing engines. So the one that are consuming fuel on air, so the one that are used by aircraft engines. I will divide my presentation in two parts. So the first one is more about a reminder because it's about the basics of chemistry, and more specifically the basics of thermochemistry. So I will be back on mass balance, on specifically on the equation, chemical equation, energy balance, and some fundamental concept which is really important for us, which is called the adiabatic flame temperature. And after that, the second part will be a little bit more applied because I will explain how to practically manage this kind of concept, but in the specific case of an engine. This situation, the engines is the one that are used by aircraft, and so how to, for example, decide or to tune exactly the amount of air we want in order to supply the combustion process we are dealing with. Okay, so some few basics reminders of what a combustion process is. A combustion process, basically, it's a chemical reaction that involves so a change in the chemical composition of an amount of matter, which is usually gas. And this in this reaction, specific component, which is from a chemistry point of view called the reductant, but for us it's fuel, will give electrons to another component, which is another reactant. And from the point of view of chemist, it's called an accident. For us, it's a combustive, and we will see that it's mostly air and oxygen on air. Oxygen specifically. And so we combine a fuel and a combustive in order to produce some exhaust gas. And I will be back on the exact composition of this exhaust gas. The thing is, this kind of reaction is called exothermic because the enthalpy of the uh, product of the reaction is actually the sum of the enthalpies of the product of reaction is actually lower than the sum of the enthalpy of the reactants. And so you have a decrease of the enthalpy all along the process. On this decrease of enthalpy, I will get back on the detail on the equation related to that in the rest, can be used, for example, to release some heat. It's not the only use we can do of this kind of chemical reaction, but it is the way it is defined. And so it's why we are talking about exothermic reaction. It's possible to extract some heat from this reaction, even if in our application, or specifically for this afternoon, we will not really release heat from this reaction. We will just use this variation of enthalpy in order to increase the temperature of the gas flow of the exhaust gas stream. For we will consider this kind of process, but mostly from the point of view of engineers. And so for us, the reactant will be the fuel, the one we have to pay for, and the one we will have to carry on board inside the engines, inside the airplane, the aircraft, on the combustive, which is oxygen of air. And this one is free, this one is available outside, and we will aspirate this inside the engine in order to supply the combustion process and in order to produce the useful effect we want in order to create thrust for the complete aircraft. Um, for the fuel, so from the general point of view of combustion, it's possible to consider liquid or gases or even solid fuels, depending on the kind of specific application you are working on. For us, for vehicles in general, most of these fuels are liquid. Okay, so for internal combustion engine, so the one that are used to propel, for example, any kind of road vehicles, so the car or the trucks, this fuel is liquid, and this fuel can be gasoline for um, what is called spark ignition engine, on which is called diesel fuel. The usual word is diesel fuel. It's a little bit heavier as a chemical composition. This one is used for larger engines that are called diesel engines. And for aircraft, this fuel is called kerosene. It's not so different from the diesel fuel. This chemical composition is somewhere between the gasoline of the light vehicles and of the diesel fuel of the heavy vehicles. So far, we use almost only liquid fuels because this kind of fuel is really useful because it's really dense, and so you can transport a lot of chemical energy in a limited volume. Because of the what is called usually the energy transition, we will need to go to more renewable fuels. Okay, these fuels usually are more gaseous because it's really simpler to synthesize. It's really easier to produce a gaseous fuel than to produce a liquid fuel. There is some possibility using some specific chemical process, for example, to produce synthetic uh, liquid methane. But it's really complicated and probably it's really expensive. This is the reason why, specifically in the aerospace industry, a lot of people are starting to work on the use of gaseous fuel for this kind of aircraft. And probably the most famous of all of this fuel is hydrogen, and it's quite fashion currently because a lot of announcement has been done in the previous weeks about the future use of hydrogen into airplanes. There's a lot of trouble that goes with this kind of fuel because it's gas and it's really complicated to transport a lot of chemical energy in a limited volume, because either you need to increase the pressure to an order of magnitude which is 4 to 500, sometimes to 700 bars of pressure. So it's really high, and so the reservoirs that are transporting this fuel are really complicated to manage. Or the other way to do so is to liquefy this fuel, so to decrease the temperature in a tank which is called a cryogenic tank. So you decrease the temperature until you reach the temperature at which the gas is just liquefying. Also, you can increase the density. Also, in the same volume, you can transport a lot of energy. It's exactly the way it works, for example, for rocket engines. But it's also really complicated because we need to have some really efficient thermal insulation all around the tank in order to limit the exchange of heat with the outside, and so to maintain the fuel as a liquid. And also because we need a large refrigeration system in order to take this gas and to decrease its temperature until reaching the temperature at which this gas is liquid. Also, it's usually used in rockets, but the thing is, a rocket, the duration of the flight for a rocket, as you know now, is the order of magnitude is minutes, 2 to 3 minutes in order to reach the lower orbit. So it's not really complicated to use in such kind of situation. If we want to use exactly the same kind of tank, but with an aircraft, we will need to maintain this lower temperature inside the tank for dozens of hours. And it's really complicated to do so. It means also to carry on board a lot of equipment, a lot of devices, and so it's a lot of weight which is added in the aircraft. Also, it's a lot of fuel in order to transport this this weight. It's a really complicated question. So I will, in the rest of the explanation, I will specifically focus on liquid fuels because it's what is usually used in current aircraft. But I will also talk about gaseous fuel because it's future fuels. On the last kind of fuel, which are used but not for transportation, it's solid fuels. So you can imagine coal for the production of electricity, sadly, or wood as a pellet, or even the wood you are using for barbecue. It's another kind of combustion process, but it's not used for vehicles for a reason you can, I think, easily imagine. For the oxidizer or for the combustive, oxidizer on combustive is the same sense. Usually we are using air, the oxygen of air to be more accurate, because this one is free. So you just have to aspirate some air and to combine the oxygen of the air with the fuel in order to obtain what you want. And in some specific application, and so for example in rocket engines, we are also using liquid oxygen because in this case, for a reason which in my opinion is obvious for you because we already talked about that. A rocket is supposed to work also into vacuum, so into space, so in a place where there is no air, there is no oxygen you can aspirate from the outside. And so you need to carry on board all the oxygen you need for the combustion process. And this is the reason why, and I will be back on this on the next lesson, next session, both fuel and combustive needs to be carried on board in rocket engine. So rocket engine are the type of system that are using pure oxygen along their combustion processes. But most of the time, and specifically for this afternoon, this combustive will be the oxygen of air. Chemical energy, and I will be back on how it works, that is released by the combustion process can be used, for example, to produce heat in two different ways. On this heat can be used, for example, to produce some work after that. It's pretty much what will happen in our engine for this afternoon, but it can also be used directly inside the system. Inside, for example, a variable volume, it's exactly what happens inside an internal combustion engine. So there is different ways to use this chemical energy in order to produce useful work. Some few information about combustion processes. It's really, really complicated. Really complicated. If you want to go into the details of any kind of combustion process, even the simplest one, you will have hundreds of different reactions that are occurring at the same time, that are consuming the same reactant, that are producing different products. So it's horribly complicated to go into the detail of chemistry. Hopefully, it's not really needed for what we need for the rest of the lecture, because we are only interested into the energy related problem, the energy related parameters. So we just need to know to calculate the efficiency, the thrust, on the fuel consumption of the engine. Only things that are related to energy. And in this situation, we will only consider one reaction or two reactions depending on the composition of the fuel. And it's the reason why it's possible for us to talk about that. But for example, if you want to not only talk about energy, but also talk about pollutions, so the kind of pollutant which are produced by combustion processes, which is an issue specifically for internal combustion engine, because this kind of pollution, it's at the level of the ground, and we have to sometimes we breathe this kind of pollution, and it's why it's dangerous for us, for climate and everything. If we want to calculate the exact amount of pollutant, and some of them are produced in really tiny amounts in the exhaust gas, this calculation is really complicated, because you need to take into account at the same time all the chemical composition, all the chemical reaction that are occurring inside the volume of gas. And this one is really complicated, but actually it's two different jobs. You have the job which is related to energy, so the one we are interested in, the one I'm able to explain to you, because all which is related to pollution, honestly, it's really too complicated for me. It's not my job. And the second job is the one of the chemist that are interesting into, for example, the pollution. And these guys have to take into account all of this relation, all of this equation. And this calculation is really complicated. For an order of magnitude, I just saw a video on YouTube yesterday about this. An engine, an internal combustion engine that usually works, will have a complete revolution, for example, in 1/10 of a second. So 1/10 of a second to, for example, to have a complete revolution of the shaft. If you want to simulate uh, all the chemical reaction that occur in the volume of gas which is contained in the engine, and you have a supercomputer, not our computers that are really designed to make a lot of calculation, it's 24 hours. Another parameter which is complicated with combustion process is that some of them are using catalyst. I won't be back on catalyst because it's not really used for this kind of combustion, but you have to know that this kind of system exists. A catalyst is a specific device. Sometimes it's just a layer of some metal materials, which is on a surface. This catalyst is used in order to facilitate the combustion process, and so to decrease what is called the activation energy. So the energy barrier you just need to go onto in order to trigger the combustion process. Okay, taking into account this catalyst is really complicated also, and as I just explained, the most complicated situation is when you have to deal with internal combustion engine. So it's noted ICE in the rest of the slides, because at the same time you have a change of chemical composition, obviously, but also of volume. So you change the volume, you change the pressure, you change the chemical composition, and so you change the temperature, and it's horribly complicated. Or for this afternoon at least, it's it will be more simple. For a really good reason, we will only consider open combustion processes. So it's in a defined volume, it's an open system. You just inject some fuel, you produce the flame. And so at the outlet of the system, you have your exhaust gas, which goes on the rest of the system. And it's simpler to design. The Even the complete calculation of pollutant in this kind of combustion is simpler than the one in internal combustion engine. Next one, so how to uh, practically explain or quickly explain how this kind of system work. Once again, you have a chemical reaction which occurs inside something which is called a combustion chamber, and for us it's a sort of cylinder, and you just put some fuel on combustive. And so in this chemical reaction, we have the fuel which is supplied in that. You have an oxidizer. Our main job as an engineer will be to adjust exactly the amount of fuel on oxidizer in order to obtain what we want. And what we want in the rest will be the temperature of the exhaust gas, because it's a really fundamental parameter for the performance and at the same time for the operating life of the engine. And so you are mixing fuel and oxidizer, you have some chemical reaction that occur inside your combustion process, and you are producing some exhaust. And for us, it's exhaust gas. In some specific case, it's possible to have some liquid. I will be back on this, but usually it's water. But it's the reason why I will only talk about gas stream or gas flow, because exhaust is only as a gas. It corresponds from the point of view of chemistry to the product of the reaction. Okay, so we mix some fuel on oxidizer, on combustive, so it's called reactant. And this reactant are just combining inside the combustion process, and we are producing products of reaction. And these products of reaction, in the language of engineers, it's exhaust gas. Okay. On this enthalpy variation, actually, for useful purpose, so for the purpose of producing something which is useful for us, can be done in three different ways. The first way is the one we will consider in this afternoon. So we just heat up the gas stream. So you imagine your chemical process, your combustion process occur in a combustion chamber, and we try to make it as more adiabatic as possible with no exchange of heat with the outside. And so all of this chemical energy which is released by the combustion process is just embedded inside the system. It's just enclosed in the system. And so the only way to balance this and to use this energy is to increase the exhaust temperature. It's exactly how it works in the aircraft engine. We will discuss about in the rest, and also in gas turbines, which are systems that are really close to aircraft engine. It's just they are designed to produce a mechanical torque, so mechanical power on the shaft rather than kinetic energy on the gas. But the structure of the system, it's really close. The other way to use this kind of combustion process is to make them work at a sort of constant temperature and to extract the heat. And so you are combining the fuel on the combustive, your combustion process is occurring, but your system is not isolated. The heat is extracted from this combustion process, for example, in order to heat up another fuel, another fluid. And the last way to do so is to have this kind of combustion process, but it's inside a varying volume. And so this variation of enthalpy is used in order to increase the pressure inside the volume. And this increase of pressure will create a variation of volume, and so you are producing work. It's exactly how it works in internal combustion engine. And there is another way to do so, but I won't talk about that because it's a completely other topic. It's called fuel cell. So I guess most of you have already heard this word. For the French-speaking people, it's called pile à combustible. And fuel cells are actually maintaining two different, which are called half reaction at two different places. And this chemical reaction are just exchanging some electrons, and so you are producing directly electricity directly from this the combination of these two reactions. So it's a completely another way to work. But if some of you are interested into fuel cells, we can discuss about that because it's my former job actually, so I can speak about that for hours. If we are going more into quantitative things about a chemical process, we will need to have some relations in order to rely the amount of uh, reactant, also of fuel on oxidizer, and the amount of products that are synthesized by this kind of reaction. And for so we are considering what is called the chemical equation. Okay, so a chemical equation is just an equation exactly as this one, number one, that describe the way reactants are combining in order to produce products. Okay, and so it's why usually on the left you have what is called the reactant, and so for us it's fuel and combustive, but for any kind of other chemical reaction it could be another situation, other kind of reactant. And on the right part of the equation you have what is called an exhaust. Okay, and you have an arrow that goes from the reactant to the product. From the point of view of chemistry, it's because this kind of chemical process is irreversible. It's not possible to maintain the opposite reaction in the other sense, whereas it's possible to do so for a lot of different chemical processes, but not for combustion. Combustion process is irreversible in the sense of chemistry because once you have fuel and combustive, you are making them react and you will produce some exhaust gas. But it's really impossible, or even if you are supplying some energy to the product and it's really complicated to get back to the reactant. So it's why there is a simple arrows. And from a mathematical point of view, the big R here corresponds to the list of reactants. So for us, it will be mostly fuel, combustive, and some gas which are combined with that but are not participating or are not supposed to participate to the chemical reaction. And P is the list of the products, and for us, it will be mostly carbon dioxide and water. Okay, and if once again you are interested into pollution problem. So with a lot of this kind of equation, you will also have to take into account as a products, I don't know, maybe nitrogen oxide, carbon monoxide on all of these pollutants. Okay, so practically here on equation 2, you have the example with the combustion of methane, okay, which is the simplest of the hydrocarbons component because it's only one carbon atom with 4 atoms of hydrogen. And if we want to consume this fuel completely, you will need to combine it with 2 molecules of oxygen. So, okay, so it's 1 molecule of fuel of methane, so 1 mole of methane, which need to be combined with 1 molecule of oxygen, 2 molecules, sorry, of oxygen, and so 2 moles of oxygen. And if you are combining them on your system, your combustion is said complete, at the end you will obtain 2 different products. You will obtain 1 molecule of carbon dioxide and 2 molecules of water, or 1 mole of carbon dioxide on 2 moles of water. And the thing is, in this case, these relations are only of a molar nature. Okay, I will be back on all which is related to mass because from a practical point of view, in engineering, we prefer to work with mass, with kilograms of fuel. But in this specific case, because it's only a specific number of molecule with a specific number of molecule, or a specific number of moles with a specific number of moles, it's only about molar quantities. Okay, on this specific number are called stoichiometric coefficient. Okay, so if you take a look again at this reaction, you will see that you have the stoichiometric coefficient of methane, which is equal to 1 for a really good reason. It's why it's because it's fuel. Okay, on conventionally in engineering combustion, fuel is the component we have to pay for. Also, it's the one which is sometimes really expensive. Also, it's the reference component. Also, we, by definition, the stoichiometric coefficient of fuel in combustion engineering, it's always equal to 1. It's unity, always. On all the other stoichiometric coefficient are calculated considering that the one of the fuel is equal to 1. Okay. Also, in the case of methane, the one of oxygen is 2, on the one of carbon dioxide is 1, on the one of water is 2. Okay. If you just take a look at this equation, you can imagine, for example, to multiply this equation by any kind of number. And so I can, for example, write 2 molecules of methane and 4 molecules of oxygen give 2 molecules of carbon dioxide and 4 molecules of water. It's exactly the same. Okay, so there's a sort of infinite number of different chemical reactions that are giving the same results. It's just the convention in combustion, specifically in engineering, is to consider that the stoichiometric coefficient of the fuel, so the component we have to pay for, is always equal to 1. As I explained, in such a combustion process, all the quantities of reactant or products are linked to each other by amount units. But the thing is, in engineering, we always have to deal with mass-related amount of matter. So it means when you are buying some fuel, you will buy it at a kilogram more practically probably at a ton, but it doesn't matter. It's only with mass. So outside of the combustion process, all the calculations are done in kilogram, in mass units. And this is the reason why we need this kind of relation. So relation 3 on 4 are actually exactly the same. They are the kind of relation we can use in order to to establish the link between the mass flow rate of, for example, reactant here in blue or product here in red, related this one to the mass flow rate of the fuel. The only difference between these two last relation, relation 3, equation 3 and equation 4, is about the minus sign. It's just a convention of sign, okay? Because from the point of view of thermodynamics, all which is going into the combustion process is count as positive, okay? It's always the same convention of sign. And so it's why the reactant between them are linked to each other with positive sign, but the product, on the contrary, is rejected, so it is lost by the combustion process, and so it's counted as negative. Okay, so for mass balance, we have all we need. The next aspect of this combustion process is about energy, because this kind of reaction is used in order to release some chemical energy and to convert it into something else. And for so, and specifically in this case, I will only consider some open system. Okay, so system that are exchanging continuously some gas with the outside. So I will just show you an example of how to do so. So in this system, specifically on the rest, I will consider that my combustion chamber is just a sort of cylinder here, which is supplied by a fuel. So usually the fuel is injected this way inside the system. And if you take a look at actual combustion processes, you have some holes that are drilled in the outside surface of the combustion chamber, and the air is entering this way. Okay, and it's mixed with fuel. On inside this system, you have a flame which is produced. Okay, so the flame usually looks like this. You have a beautiful flame. On the end, you will produce some exhaust. Okay, so the exhaust is here. Okay, so you have a mass flow rate of exhaust, you have a mass flow rate of fuel, and you also have a mass flow rate of air, which is here. This system is open. Okay, it's open, is a constant volume, and so there is no possibility to exchange any pressure work with this system. And so this is the reason why when I will describe this on using thermodynamics, I will consider the formalism which is related to open systems, so the one which is based on enthalpy. Okay, if I just go back on this, the variation of heat, the exchange of heat, which is released by the system, because there is no possible work which is exchanged with the outside, is due to the variation of enthalpy. Okay, so in my volume here, inside my system, here, my control volume is all which is inside this combustion chamber. In this combustion chamber, if I apply the first law of thermodynamics, I will obtain a variation of enthalpy because my system is open. So it's not internal energy anymore, it's enthalpy. Just remind your lecturer of thermodynamics. It's equal to the exchange of heat. Because there is no work exchange, there is no variation of volume. Okay, pressure work is related to volume variation. If you don't have any variation of volume, no work. In this equation, the variation of enthalpy is actually only due to the change of chemical composition. Okay, what happens inside this volume of gas is a chemical reaction, and a chemical reaction is a change in chemical composition. So basically, probably in a really simpler or simplest way to explain this, you have an initial mix of air and fuel, on only that, and you have a combustion process that occurs. So progressively, the time needed for the combustion process to be achieved, you will have a progressive increase of the quantity of carbon dioxide on water vapor. At this level of temperature, it's only water vapor. And so you change progressively the chemical composition of your mix until you reach a complete reaction with no fuel anymore, because fuel is paid. So we need to consume it completely. And so you will have a progressive change in the chemical composition of the system, and it will correspond to a change of enthalpy. Okay, so if I get back to my equations, I just see that I have the variation, the elementary variation of enthalpy of the system, which is due to the change of its chemical composition. Each of the component inside the combustion process, so namely fuel and combustive, have their own specific enthalpy. So you have 1 mole of fuel that corresponds to one amount of enthalpy. You have 2 moles, for example, of combustive, if we are using the example of methane, and to these 2 moles with corresponds another amount of enthalpy. And you change this chemical composition, and you will produce, for example, carbon dioxide and water vapor. But carbon dioxide and water vapor have other values, have other enthalpies, because it's not exactly the same component. And so if you change the chemical composition of the system, you will also change the enthalpy of the system. And this is this variation of enthalpy which is used in order to produce work, and which is used to produce something else at the end of the process. Also, more formally, if I consider this equation, combining this this first law balance with the previous relation that were implying the amount of mass of a mass on mole, so equation 3 and 4. I include equation 3 and 4 in the first law of thermodynamics, and at the end I can obtain an expression of the heat which is released by the combustion process, which is only the product of two things: the amount of fuel which is consumed, and the other one is a parameter which is called heat of reaction, or enthalpy of reaction, or heat of combustion, very different expression, different way to name it. And this one is only related to the combustion process itself. And so for a specific combustion process, you have a heat of reaction, and I will explain just after that how to calculate this. On this heat of reaction, when you multiply this by the amount of fuel that has been consumed, you obtain the heat which is finally released by the system, if your system is supposed to exchange some heat with the outside. Or you have the variation of enthalpy, which is used to increase the temperature of the exhaust gas, if it's exactly what you want to do. The relation is really not complicated. And at the end, we will obtain exactly for the same reason some relation that which is implying the mass, because it's more practical, on the a parameter which is depending only on the fuel itself, in order to obtain the heat produced. Okay, so it's always about the reaction, about the amount of fuel which is combined, and you make it work, you multiply this, and you obtain the heat which is supposed to be released. Um, so how to calculate this heat of reaction? It's not really complicated. The idea is we have a sort of specific algorithm to do so. We are starting from elementary reaction in order to calculate the specific enthalpies of the component. So let's consider, for example, the same equation we previously had, the one which is involving methane. Okay, so I know I have one molecule or 1 mole of methane, which is combined with 2 moles of oxygen in order to produce 1 mole of carbon dioxide plus 2 mole of water. And by definition, the heat of reaction, so the heat which is released by this combustion, is the difference between the enthalpy of the product and the enthalpy of the reactant. We need to calculate the enthalpy of the reactant and the enthalpy of the product in order to obtain the amount of heat which is released by the combustion. And so we need to know all the enthalpies of these components. And by definition, all the simple and stable components are supposed to have a specific enthalpy which is equal to 0. Actually, enthalpy is exactly as energy. There is no absolute value. It's only about reference value. We decide of the reference and that's it. And so the convention in chemistry is to suppose that the standard state is 1 atmosphere of pressure and 25 degrees Celsius of temperature. This is the standard state. And at this standard state, we decide by convention that some simple component have a specific enthalpy of formation, which is equal to 0. And this is the starting point. And in this case, in the case of my equation, the only example of that is pure oxygen. Okay, so I didn't add some information. I suppose that the methane is a gas, that oxygen is a gas, CO2 is always gas. And for water vapor, it's quite more complicated, but I will be back on this. Let us suppose it's only gas for the moment. Pure oxygen as a gas, by definition, because it's a stable and simple component, we suppose its enthalpy is equal to 0. Okay, it's just a reference value. And so I can note that in this case, the enthalpy with the bar, the below bar is just for the molar notation. It's the choice I made of molar notation because in thermodynamics we usually deal with mass enthalpies, and so my default enthalpy is in mass. It's always suffering for me to work with molar quantities because I'm not a chemist, and so to just make the difference and avoid any confusion between these two notation, I just use an underline H. So underline H, the zero subscript means standard, okay, of oxygen as a gas is by definition 0 joule per mole. I want, for example, to obtain the enthalpy of carbon dioxide here. But this one is not a simple component. Carbon dioxide is a quite more complicated component. And so I will need to consider a specific reaction that produce this chemical component. And so this one is not really complicated. It's just the combustion of uh, carbon. Okay, so you have carbon as a solid, okay, as coal, for example, and you burn it with pure oxygen in order to obtain carbon dioxide. These two components here are simple. Okay, so this one we know it's already equal to 0 because I already know this in the previous equation. So it's 0 joule per mole as an enthalpy. This one also is a stable form of carbon. And so it means that this specific enthalpy of carbon as a solid is also equal to 0 joule per mole. I just need to know now the value of the one of the CO2, which is, by the way, also produced as a gas. In such a situation is not complicated. I just make an experiment. I won't do so actually because a lot of people already did that in the past using some specific system that are called calorimeter. Okay, a calorimeter is a sort of box in which you have this kind of reaction, and there is a specific experimental device that allow you to calculate the amount of heat which is practically released. Okay, and so you have, for example, a specific amount of carbon, you know, exactly the amount of oxygen you need to burn this, and you make this system work, and actually you compensate the heat which is released in order to maintain the temperature all along the process. And after that, you can measure the amount of heat that has been released by the system. And if I do so, I will obtain a value which is the heat, which is calculated using a calorimeter, is counted as negative because it's released. Okay, it's an exothermic reaction, and so it's minus 393 kilojoule per mole. This is the heat of reaction that has been measured. And so, because I know the heat of reaction which is released when I combine carbon and oxygen in order to obtain carbon dioxide, and I know that the enthalpies of the reactant are equal to 0 by definition because it's simple components, I can obtain from that the what is called the enthalpy of formation. I will try to not make any mistake in the notation because I'm not really good at that. So this one is known. Good. I have the answer for this part. Now, how to do so for water? It's exactly the same. I will consider a simple chemical equation that produced water and only water. It's really important. So for this one, I will consider this. How to do so? Not complicated. Just hydrogen, some hydrogen as a gas, and you mix it with half of a mole of oxygen, still as a gas, and you will obtain 1 mole of water. Okay, and let us suppose it's still at gas. It's another experiment. It's another chemical reaction. Probably you will you will make work in another calorimeter, or in the same, it doesn't really matter. You can imagine you have another calorimeter, which is this one, and this one is used for hydrogen. Let us imagine it's not exactly the same. Once again, the two reactants are simple. So it means that this one is known, it's already equal to 0. And hydrogen as a gas, it's in its stable form. So we suppose at 25 degrees on 1 atmosphere, its specific standard enthalpy is equal to 0. Okay, so H standard of hydrogen as a gas is equal to 0 kilojoule per mole. This one is still equal to 0. I make it work in a calorimeter, and I will obtain a rejection of heat using another calorimeter. On this rejection of heat, this one is supposed to know by heart because I worked a lot on hydrogen in the past, but I forgot it actually. It corresponds to 242 kilojoule per mole. On using exactly the same process, now I know because this specific enthalpies are equal to 0, then the enthalpy of formation of water is equal to this. The enthalpy of formation of water as a gas, up, up, is this. Now I know this. On this value, it's just getting back into my equation. Okay, and now I know the enthalpy of formation of carbon dioxide on water. And I also know the enthalpy of oxygen. So in combining this, it's possible to calculate the one of methane because I do the same kind of combustion process inside the calorimeter. Combining different chemical reaction, not exactly the same, in different situation, in different reaction, on step by step, we build a sort of structure inside which you have all the values of the specific heat of reaction. Okay, on the example of specific heat of reaction are exactly coming from this kind of reference value. You have a reference value. The conservation of energy is still valuable. It's always valuable. And so it means that the heat you will release in burning some specific component is exactly the same as the heat you need to supply in order to produce this component from the same product. So you can imagine that this reaction is actually reversible, which is true in a specific calorimeter. It's not true in a combustion process because it's not designed for so. But in a calorimeter, we can do so. And so it's reversible, and because it's reversible and because you have a conservation of energy, the amount of heat which is released by the combustion process is exactly the same as the heat you need to supply to the product in order to get back to the component, to the reactants. Okay, and so using that, it's possible to combine with different experiments and obtain all the heat of reaction you need to know for any kind of fuel. And so when you have a specific fuel and you have a specific chemical composition, usually you already have the values. You just take a look at Wikipedia. You have a large table with a lot of heat of reaction values for a specific fuel. But it's also possible for a new fuel to just decompose it in some specific chemical reaction and to get back from the enthalpy of formation of simple components or even more complicated components through their values in order to get back to the heat of formation of your fuel and so to the heat of reaction. And so from that, we have the standard value. So it's possible now to go to the next step with some example of standard heat of combustion. So standard heat of combustion, it's named this way because it's standard as temperature and pressure. So we suppose the pressure is 1 atmosphere and the temperature is 25 degrees. But the thing is, we are not interested into molar quantities for a really good reason. You will never buy some fuel in molar quantities. Everything is bought in kilogram. Okay, so the unit, the physical unit of reference is kilogram. And so we need to express this heat of reaction. So once again, the ability of a specific chemical reaction to release some heat, but to express it with mass as the amount of matter, as the way to quantify, to assess the amount of matter involved. And for so, we introduce another concept, a new concept, which is specific to engineering chemistry, heating value. So is by definition the amount of heat which is released by a combustion process when 1 kilogram of fuel is burnt. Okay, so it's not 1 mole anymore, it's 1 kilogram. And so it's a technical parameter which is fundamental because for any kind of fuel you need to know, you need to calculate the value of this heating value. And so to express it more formally, it's just equation 6. Okay, the heating value is the amount of heat which is released divided by the amount of fuel involved in mass. And when you combine everything, at the end you just obtain the ratio of the heat of reaction, of the enthalpy of reaction divided by the molar mass of the fuel. Some important detail, by definition in chemistry, for an exothermic reaction, it's not complicated to demonstrate. The enthalpy of variation of an exothermic reaction is negative. But in engineering, we don't like to manipulate this kind of negative sign because it's a source of mistake we suppose it's positive. And so a heating value is always a positive value. And so there is no minus sign. And so when you are going from the heat of reaction to the to the heating value, you use absolute value because it's always a positive. Okay, now another detail. It's not really complicated, but you will need to focus for a few minutes. As I already explained, in any kind of combustion reaction, and specifically the one that are involving hydrocarbons, the first component in quantity which is produced by the reaction is water. Okay, so your reaction is producing water vapor. If you are rejecting this vapor directly in the surrounding into the air, and you are just using the heat which is produced by the reaction, you will have a specific value of the heating value. Okay, it's basic heat which is released by the combustion of 1 kilogram of fuel. That's it. Now imagine that the water vapor you have in your exhaust gas, you make it condensate, you make it liquefy. This kind of reaction will release some heat. And so it's possible to extract some heat from that. So if I get back to my combustion process, I have some water vapor and I make it condensate, I will I will absorb the heat of the reaction on the heat of the condensation of water. And so I will get back more heat than in the situation where my water is only produced as vapor. So in this second reaction, in this second situation, we talk about a higher heating value, the HHV. This is the reason why we have two different values of the heating value. You have the lower heating value for the one we are interested in for engine, on the higher heating value, which is mostly used, for example, for heating earth system in buildings, because in some cases it's possible with the exhaust gas to just liquefy water and increase the amount of heat which is get back in order to heat up the building. So in this case, we are talking about higher heating value. To finish with that, an example on the last line, if I consider the heat of reaction I previously calculated for methane, and I divide it by the molar mass of methane, I will obtain what is called the heating value, the lower heating value of methane. It's close to 50 megajoule per kilogram. If I remember well, it's here. Okay, here you have some example of lower heating value in the second column. On the third column, it's about higher heating value. It's really close. It's between 40 to 50 for most of hydrocarbons. The only exception, and it's quite clear in this table, is hydrogen. Hydrogen will release a lot of energy. But at the same time, keep in mind that hydrogen, it's really not dense. It's a really dilute gas. It's really complicated to have a large amount of hydrogen in the same volume. And so if you want to produce the same amount of heat for the same combustion, in replacing, for example, hydrocarbon by hydrogen, you will need to increase a lot the pressure in the tank of hydrogen. And so the heat which is released when it is divided not by the mass but by the volume is really not so favorable to hydrogen. Few minutes back on the basic performance criteria we already considered in the first lecture, if you remember, all which was related to flight. I already and we already worked on the propulsion efficiency, so I absolutely sure it's completely clear for all of you. But there was another efficiency which was related only to the engine itself, which was called thermal efficiency. And I explained quite quickly that this thermal efficiency is just the ratio of the rate of increase of kinetic energy, so the useful effect which is supplied to the gas which is ejected, which is released by the engine in order to produce thrust, over the chemical energy or the heat energy which is used for so. And actually, this chemical energy, now we have a way to express it, and it's just expressed as the product of the mass flow rate of fuel by the lower heating value. Okay, so it really corresponds to the rate at which the chemical power is consumed, and so the rate at which the heat is released in sort of way by the combustion process. Okay, and so now using, for example, the formula number 9 on the lower part of this slide, it's completely possible to calculate the overall efficiency of an aircraft, considering at the same time the propulsion one, which is due to the design of the engine, and the thermal one, which is due to the performance of its engine. Okay, the rate at which the chemical energy is supplied to the engine now is just the product of the mass flow rate by the lower heating value of the fuel. the adiabatic flame temperature. So it's the time for a new drawing. Okay. I spent a lot of time to just set up all of this camera, so now I need to enjoy it. Um, as I explained, in the combustion process we will deal with in our application, these systems are open. So once again, you have this combustion chamber, okay, which is supplied by fuel and combustive, so air, for example, which is arriving here, and the exhaust gas is getting here. The exhaust gas, in our case, is the working gas. And actually, the higher its temperature, the higher the amount of work we can extract from this gas. What we need to do is to increase as much as possible the flame temperature from the inlet of the system to its outlet. So quickly, you just imagine you have the temperature here. You have, for example, the entrance of the combustion process here, and you have the outlet part here. And the goal for our system is to increase as much as possible. So here you can imagine the temperature of the fuel or the temperature of the air at the inlet of the combustion chamber. And we will use this heat of reaction, this variation of enthalpy, to increase as much as possible the outlet temperature. Okay, and this temperature here is the flame temperature. From the only point of view, for the sole point of view of efficiency, the higher the better. Okay. In practical situation, we will need to dilute this combustion, because if not, we'll just destroy the engine so quickly it won't be really practically useful. But from just letting this on the side for the moment, just about energy, the higher the temperature, the better. In such a situation, the maximum value of the flame temperature we can reach is the one that corresponds to an adiabatic, a real adiabatic combustion process. Okay, so you imagine you have your combustion chamber, which is completely isolated with no exchange of heat with the outside, no heat. So the only way for this variation of enthalpy to be extract is into increasing the enthalpy, also the temperature of the gas which is getting out. The maximum temperature of the flame is called adiabatic flame temperature. Okay, by definition, this one is really the maximum one we can imagine to reach, and it corresponds to adiabatic and ideal flame temperature. Actually, it will be different for two reasons. It's actually impossible to have a completely ideally adiabatic combustion process. It's not possible to have this kind of system, even if the efficiency of this kind of combustion chamber is really high. So usually for the best system, we will just lose 5% of the initial chemical energy. And so this efficiency are really close to 95%, which is really high. And the second reason is we don't want to reach this kind of temperature. Just take a look at this here. You have the order of magnitude of the temperature of the combustion process. So for example, for methane and pure oxygen in stoichiometric combustion, and you just let things go and let temperature rise, you will obtain outlet temperature which is higher than 2800 degrees. So for a stationary flame, there is no system that resists to this, or it will be probably really too expensive and impossible to use on practical application. And so we will need to dilute this. It's exactly the same for air. For example, consider here you have methane, you mix methane with air, so with oxygen and nitrogen, you make them burn in a completely adiabatic system. Also, you will reach a temperature of almost 2000 degrees. And for a lot of practical application in gas turbine and in aircraft engine, this is really too high, because your system is supposed to work. Just keep in mind in my previous drawing, the flame here is permanently present inside the combustion system. And so it means that you will have a permanent exchange of heat from the flame to the inner surface of the combustion process. And if you maintain 2000 degrees of the flame at some centimeters away from the inner surface of the combustion chamber, you will destroy everything. And it won't be possible to work for 12 hours, for example, as it is needed for typically for an aircraft, and certainly not for hundreds or thousands of hours as it is needed for what is called heavy-duty gas turbines, so the gas turbines that are used to produce electricity. So in all of these situations, the way we are solving it is to dilute the combustion. So I will be back on this at the end of the lecture in injecting more air than when it's needed. And so at the end, the actual temperature of the gas will be, for example, this. I have an actual flame temperature, and we decide of this flame temperature. Okay, so now the practical aspect of combustion processes, because all I explained was about simplified combustion process with a fuel, a combustive, stoichiometric combustion, and okay, simplified version. It doesn't work. It absolutely does not work this way on practical combustion processes. The first reason is it's not really possible to just have oxygen which is absorbed in the combustion process without nitrogen. And this is the reason why, and take a look at equation 11. This is the equation, the complete equation of an hydrocarbon. It's a little bit more complicated than an hydrocarbon fuel because the fuel can also contain some oxygen and nitrogen. So this way it's possible to consider, for example, ammonia. I have the stoichiometric coefficient of oxygen on oxygen. On oxygen always come with some nitrogen. And I know that in here, whatever is the temperature of the pressure, I always have 21% of oxygen and 79% of nitrogen. Okay, this is the standard air we will use in the rest of this combustion. And the thing is, because you have 21% of oxygen and 79% of nitrogen, when you have 1 mole, it's in molar fraction. When you have 1 mole of oxygen, you always have 3.7576 moles of nitrogen. So the calculation is really not complicated, but it's important for you to have seen it at least once. Okay, so in air, I know that oxygen is present at a level of 21% in molar fraction. Okay, and the simplified air is with 79% of hydrogen in molar fraction. And now what I want is to have 1 mole of oxygen, or 1 molecular amount of oxygen. So I need to have, so this one is obviously equal to 0.21 and 0.79. If I want here to have 1, I just need to divide 0.21 by 0.21. This is high-level mathematics. Please focus, it's complicated. And so it means that here I will have 0.79 divided by 0.21, okay? Because this one is just this. Okay, I just multiply. I just divide, in this case, by 0.21. And so this one is just equal to 3.76. This is the reason why in such kind of combustion process, when I have 1 amount of oxygen, I have 3.76 amount of nitrogen. And this is what is called alpha in my slides. From that, I have the fuel, I have the combustive. So combustive now, from a strictly speaking, from the strict point of view of chemistry, it's only oxygen. But remember that oxygen never comes alone. It always comes with this nitrogen friend, and so you have to deal with both at the same time. And when you combine fuel and combustive, you will obtain always carbon dioxide, water, okay, and the stoichiometric coefficient of water and carbon dioxide is not complicated to calculate. It's you just use the formula in order to obtain so. Also nitrogen, because nitrogen is not supposed to be involved in the combustion, so it's get in and it get out. And because of the conservation of mass, you will have the same amount of nitrogen which is going in than the one which is just rejected by the combustion process. So it's why I called it non-reactive nitrogen. And the last component is oxygen, because if your combustion is consuming more air and so more oxygen than when it's needed, you will still have some oxygen at the end, because not all of the oxygen is consumed. In a simple way, just imagine you have what is called the lean combustion. I will be back on this just after that. And you inject into your combustion twice the amount of oxygen which is required for the combustion process. It means half will be consumed because it's what is needed by the fuel, and the other half will not be consumed. And so at the end, you will have in the exhaust gas half of the oxygen you had in the initial gas. And so you have a remaining part of the oxygen which is not consumed by the chemical combustion, and so it's why it's called unburnt oxygen. The thing is, for practical reason, we can have 3 different cases of combustion processes. The first one is called lean combustion process. Though the lean combustion process is when you are, it's exactly the one we have in gas turbine and is in aircraft engine. It's when you are injecting more air than when it's needed by the combustion itself. And so you have some air, and specifically some oxygen, which is not consumed at the end of the system. This one is important for this kind of systems for aircraft on gas turbine because one, it helps to maintain the temperature of the flame at a level which is compatible with the maximum temperature admissible inside the combustion process. Okay, just to remind my drawing here. And the second reason it's because we want to have all the fuel consumed. Okay, the fuel is paid, and sometimes it is expensive. It's a significant part of the economical balance of the complete business. And so we need to burn it all. The other situation, which is more rare because it's usually not good from environmental point of view, it's called rich combustion. Rich combustion means you are injecting less air than when it's needed by the combustion. So if you get how it works, it means at the end you will have some fuel that has not been burned. For most of application, we need to avoid this for different reasons. The first one is obviously you are not consuming all the fuel you are paying for, and also because you will produce a lot of pollutants. And for example, when you have some microparticles, so it's really important from an environmental point of view. Microparticles are produced by combustion engine, internal combustion engine, when they are working in a rich combustion. We try to avoid the rich combustion, but the thing is there is some specific transient phase. For example, when you change the power, you change, for example, the rotational speed of the engine, or you are just starting the engine. In this kind of transient phase, the system is evolving so quickly that the fuel injection system doesn't have enough time to just follow the rhythm, follow the rate at which the gas is consumed. And so, for a few seconds, in the worst situation, for some minutes, you have a rich combustion. Okay, because the system is not, the control strategy has not at the time to just reach the goal, which is to maintain a specific level of ratio between air and fuel. In this case, it's rich, and it's really dangerous because it will produce a lot of pollutant, and we try to avoid this as much as possible. There is an exception. There is one case in which the combustion must be rich is when you have rocket engines. And I will explain this in the next lecture, so I won't explain this now, but just keep in mind that the only case where it's useful and it's quite relevant to have a rich combustion process, it's in rocket engine. But we will talk about that in the coming lecture. So practically, once again, because we are mostly dealing with mass, we need to have a criterion that could be used to control the amount of air which is mixed with the fuel along the combustion. And this parameter is called air-fuel ratio. Okay, air-fuel ratio, AFR, is by definition the ratio of the mass of air, not of oxygen, and the mass of air, which is consumed by the combustion over the mass of fuel. So it can be a mass, it can be a mass flow rate. It's exactly the same. Here I explain this as a mass flow rate, but you can explain this as mass. It doesn't really matter. It's just the ratio of the mass flow rate of air over the one of fuel. On this air-fuel ratio must be compared with the stoichiometric one. So what is the stoichiometric one? Is the AFR with the subscript ST. ST means stoichiometric. It is the amount of air you need to, in mass, you need to supply to your combustion process to have exactly the stoichiometric combustion. And when you are in stoichiometric combustion, all the fuel is consumed, and you are supposed to not have any oxygen at the end. On the specific characteristic of this air-fuel ratio is that it only depends on the chemical composition of the fuel. But just keep in mind that the air-fuel ratio, the stoichiometric air-fuel ratio, is a property of the fuel itself, whereas the air-fuel ratio, the actual air-fuel ratio, is the property of the system, and specifically depends on the way you are using it or you are manipulating it. And when you divide this air-fuel ratio by its stoichiometric value, you will have a parameter which is called lambda, and lambda is the air-fuel equivalence ratio. And this one can allow you to decide whether your combustion is rich, lean, or stoichiometric. Some example of air-fuel of stoichiometric air-fuel ratio for current fuel, so all the same, the hydrogen, the methane. Here the green line corresponds to biofuels, so the methanol, the ethanol, and the butanol, which is not well known. It's really impressive. The butanol is a really efficient fuel, but it's really complicated to produce. And you have the octane. Octane is the pure chemical component, which is really close, which is closer to the gasoline we are usually using in spark ignited engine. And after that, you have the usual gasoline, which is usually this one, on the diesel. Okay, so diesel fuel, which are used in compression ignition engines. They work in a different way. This kind of fuel is heavier with the light diesel with 12 carbons on the heavy diesel, which are close to 15 carbons. So the light diesel corresponds to the one which is consumed by trucks, broadly. And the heavy diesel are the ones that are used by ships, okay, big boats, ships. And when you want to produce some electricity, sadly, in some places, and specifically on islands, when it's isolated, they are ordering a lot of this heavy fuel. It's quite dirty, and they are burning it into big engines in order to produce electricity. To finish with that, I won't spoil my next explanation on the next lecture, but how this kind of system work really quickly. This is the fundamental structure of an aircraft engine. So you have some gas, some air, which is aspirated at point 1. It's aspirated into the compressor. It's compressed by the system in order to reach a specific pressure at point 2. This is at this high pressure that the air is mixed with fuel. Okay, so fuel is injected as high pressure and you are producing flame. So you have an increase of temperature as much as possible between 2 or 3 or on a specific temperature difference, which is a requirement of the system. This high temperature gas at point 3 is just expanded into the turbine in order to produce work. This work is entirely consumed by the compressor, and the remaining energy inside the gas is actually converted into kinetic energy. And at the end, the goal is to use a part of this chemical energy which is released by the combustion process and to transform it into kinetic energy in order to increase the speed of the gas at the end, and so to increase its kinetic energy, which is here is now V4 because it's at point 4 that we have the exhaust of the turbine. And as you know now, the final thrust you will produce if you just let on the side of the road the pressure thrust. The momentum thrust is just the difference between the rate of momentum of the air which is aspirated into the compressor, uh, the difference with the one which is rejected by the engine. Okay, so this is exactly in such kind of structure that the rest of our calculation will be done. Quite simple example of how it works here. So you are supposed to see where my mouse here is. So here on the left you have the entering part of the engine. So air is aspirated this way. It is compressed by the compressor part here. Okay, I will explain later what is the fan and what is used for. It's compressed in 2 different steps until it reaches a combustion chamber. So the combustor it's combustion process, so you are maintaining the flame, and this flame is expanded into the turbine part. Okay, so with the HP mean high pressure, so you have the high pressure part, the low pressure part. I will explain later what is a bypass duct. It's not really important for the moment, but the thing is we are compressing gas air here at high pressure. We are mixing it with the fuel inside the combustion chamber, and the exhaust gas of the combustion chamber is expanded into the turbine. And the mechanical work which is produced by the turbine is supplying the compressor, and the rest is just kinetic energy which is rejected to the outside, on which is producing the final thrust we want. And I almost finished. This is a few information I want you to remember from this lecture. I probably made my point. Thanks a lot. See you in 20 minutes.